Good day. Thanks for watching this video and studying your math with us. Please watch it carefully, understanding each step, and maybe paused, rewound, or even watched more than once. I encourage you to read the relevant sections in your textbook and those examples as well. They are different than the ones I have worked here. Finally, doing at least a representative set of exercises is recommended. So let's do some math. Today's topic is sets and operations on sets. The first example that we'll do requires us to know about a set called the natural numbers. This is sometimes called the counting numbers and is 1, 2, 3, ... meaning, and so on and so forth. So this is all the numbers that you would use to count sheep if you were trying to go to sleep. We want to characterize each set as infinite or finite. Finite means you can count them, infinite means you would never be able to finish counting them, and we want to determine whether 8 is an element of the set. That is, does 8 belong to the set? So let's look at the first example here. 5, 6, 7, ... and so on and so forth, and goes all the way up to 10. So what we would say is this is a finite set, and we would also say that certainly 8 is an element of that set. If I called this set A, then I would say 8 is an element of A. That's the Greek epsilon. This number, this set, part B, is 1, 1/2, 1/3, 1/4, and so on. The next number would be 1/5, but notice ... it never ends. So this would be an infinite set. But 8 is not an element of this set. If I call this set B, I would say 8 is not an element of B because the next one would be 1/5 and so on. All of these fractions would be less than 1. The next example, the way we would read this is the set. These are called set builder notations. The set of x such that x is a fraction between 9 and 10. Now if you start thinking about that, you could say that the first number might be 10 minus 1/2. The next number might be 10 minus 1/4, and so on and so forth. And you could see that you could have an infinite number of numbers, fractions, between these two numbers. So this would be an infinite number but 8 is not an element of, if I called this set C, I would say 8 is not an element of C because 8 is not between 9 and 10. The last example is the set of x such that x is a natural number between 7 and 8. Well, this is exactly the set 8. And so 8 is, if I call that set D, then 8 is an element of set D, and this is a finite set. So that's example 1. Now example 2 talks about listing elements of a set. We can describe a set this way, called the rule method, or we can do a roster method. Here we say, and the way we read this is the set of x such that x is a natural number between 8 and 12. So using the roster method, listing them all, I would say 9, 10, and 11. So those are the elements that belong to the set. Here we're talking about x is a natural number greater than 6 and less than 8. So you've got to be greater than 6. So this would be 7 and less than 8. There's only one natural number there, and that's the set that we would have. So we can list the elements of a set. For this third example, we need to understand what the symbol means, and it is called subset. So here we say A is a subset of B, and that means that set A is contained within set B. Note that the set B is contained in set B, and so that little line underneath means that you can be equal. So now the first example says, is the set B that we have up here, which is 3, 9, 21, and 27, is that contained in set D? Well, it's not contained in set D because 9 is an element of B, but 9 is not an element of D. So the answer here would be false. Now, is D contained in B? Well, 3 is in both sets and 27 is in both sets, so this would be true. Here we say D is not contained in set A. And when I look at set A, I see that everything that is in D is in set A. So this would be, I'm saying it's not contained, it is contained, so this would be false. And the last example starts talking about a thing called a universal set. A universal set is the set of all items, usually denoted by U, that is under consideration in the problem. So U does not equal A. What that means is that there's something in U that is not in A. And when I look at it, I can see that 39 is in U, but 39 is not in A, so this is true. Now A is contained within the universal set, however, because sets are always contained within the universal set. So that is example 3. Example 4 introduced us a topic called the complement of a set, and in our textbook this is shown as A prime. This is the set of things that are in the universal set but not in set A. If I drew a Venn diagram of that, I would draw the universal set as the big set inside is set A, but this would be all of the things that are not in any of these, that are not in A. So you're in the universal set, but you're not in A. So here in our example, we have a universal set, set A and B, and we want to find the complement of A. So this is everything that is in the universal set that's not in A. So this is 2, 4, 6, and 8. Those are the even numbers that are in there. So the complement of this set is going to be the set of 1, 3, 5, 7, and 9. Now B is a set of multiples of 3. It's 3, 6, and 9. So B prime is going to equal the set of 1, 2, 4, 5, 7, and 8. Now U prime, that's something that's, that is not in the universal set, and there's nothing in the universal set, but that ends up being what we call the null set. This is the set with no elements, and the symbol for that is phi. So phi stands for the set with no elements in it. Lastly, if I take the complement of the set with no elements in it, it's going to be the universal set. So that is example 4. Now example 5 is another operation. We talked about the operation of doing the complement. Now we talk about an operation called taking the intersection of sets. So A intersect B, this is the symbol we use for that, means that X is in A and the word A and D, simultaneously X is in B. So if I drew a Venn diagram, I would have the universal set around the outside, A and B. These are the things that are common to sets A and B. So if I start looking at these examples then, if I look at these two sets, I see the only thing that is in both of those sets is the element 30. And so that is the answer to that problem. If I look at this example, I see that 6 is in both sets, 12 is in both sets, and 18 is in both sets. So the answer to this one would be 6, 12, and 18. In this one, I have 3 elements in this set, 6, 7, and 8. I have only one element in this, the number 678, and so these two sets are called disjoint sets, and they don't intersect with one another. Their intersection is null. Example 6, we talk about another operation that is called union of two sets. And the definition of union is you take everything that is in A, or everything that is in B, or everything that is in common with A and B. So what we have here is you take everything that is in both sets. So the answer to this is I'm going to have 1, 3, 5, 6, 7, 9, and 12. because that takes everything that is in A, 1, 3, 5, 7, and 9, and I add the things in B. So 3, I don't have to list it more than once, 6, 9, and 12. So that is the union. Let's do the union of these two sets. So we're going to have 9, 10, 11, 12. Don't have to list the 10 again, and don't have to list the 12 again, but I do need to add 14 and 16 to get the union. This one, I have 2, 6, 10, 14, and here I have 4, 8, 12, and 16. So this is every other odd natural number is being added together. And so what we are going to have is, this is going to be the set 2, 4, 6, 8, 10, 12, 14, 16, and then I would do dot, dot, dot. So that's the way it is with sets and operations. Read the book, work through their examples, and do some homework. And remember that time is precious, each day must count. Doing the math will make you strong. See you later.